Thank you all for joining us. I'm very happy to introduce to you today Dr. Pavlos Papaconstadopoulos, our MPU family member. So Pavlos finished his bachelor's and master's in Greece in 2009. And a couple of years later, he came to McGill University MPU unit for his master's and then later on his PhD. His supervisor was Dr. Jan Sungent, and Pavlos, there are many of us who have worked with Pavlos closely in the past or who remember him from grad school. So it's really nice to see you back. After his PhD, Pavlos stayed at McGill for residency and continued working as a clinical physicist at the Jewish General Hospital. In 2019, Pavlos left for the Netherlands, and he worked for the as a clinical scientist, or currently he works as a clinical scientist in radiation oncology. So today he's going to tell us about some of his work that he has done in the past, as well as what he's doing now at the Netherlands Cancer Institute. So welcome, Pavlos.
Yes, hi, Marita and everyone. Thank you very much for the invitation. And it's an honor to be invited from McGill, from Montreal. That is a place that I have well in my heart. I spent many years there, as we discussed earlier, and I do miss it a lot. Hopefully in the future we'll be able to meet in person as well. But for today, I'm going to talk about the work that we did at the Netherlands Cancer Institute in Amsterdam, Netherlands, in the last about 2.5 years. And the title of my talk is Intelligent Systems for Autocontouring QA. Yeah, so I'm going to talk about a subject that you probably have heard many talks in the last years. It's about data science, machine learning, AI, big data, a lot of buzzwords. And we often see these pictures with people holding globes and self-driving cars, and it's all fantastic. We are certain that this thing is here to stay, to some form at least. We also remembered some of the old cult movies of the 50s with some fancy robots as they imagined them. So the real question is, okay, how much of this is actually happening? Is it really artificial intelligence? What can we do in radiotherapy? And I was really intrigued in the subject many years now, to the level that I decided actually to go to the Netherlands Cancer Institute and work exactly on that topic. I do find that there is a bit of a danger that we get lost within the buzzwords. And if I was to give a little bit of some success stories that we see in data science in general, I would say that we still mostly look in examples in marketing. And not only that, but most successful data science stories, I think they're actually simple models that they use basic statistics and nice visualizations to do the heavy load. And healthcare, we know that lags behind compared to these other fields. And it's not always clear for us that we either work in academic research or in the clinic, how exactly we're going to put these models in clinical practice and make this step to go beyond research. So this, in my mind, forms a gap that already existed in a way between academic research and clinical implementation. So everybody that is involved in medical physics, I think they had an interest in implementing things, but at the same time, they like doing research. So how do we bridge this gap, and what is exactly this gap? Most often, academic research focuses on a specific scientific question that will excite researchers. We prioritize impact and originality. And we spend tremendous time performing accurate experiments. And at the end, the hope is that we're going to publish our results, usually as a proof of principle study before we move to the next topic of interest. While in the clinic, we're mostly interested in solving more practical problems. We want something that's useful, something that would add value. We do care about accuracy, but we want also something that can be deployed in a reasonably fast way and improve based on user experience. And of course, we don't want to stay on the proof of principle. We want to have a general solution that would apply to other situations as well. So this gap, I think, with this data science and analytics now era that we're living is actually becoming more and more visible, because data science and analytics sort of lives in between these two worlds. And maybe some thoughts from my side of why things maybe don't get implemented. There's a different incentive, as I mentioned in the previous slide. So researchers want to publish, clinicians want to solve practical problems. There's a communication gap. Often researchers and clinicians don't talk often enough about their ideas, even though I know at McGill and at the NKI, this is mitigated to some extent since the departments are closely integrated. But more importantly, I think last 2 points are the implementation problems. So we write a lot of research software, but often this software is not robust, it's not scalable. We don't focus too much on generalizing beyond the proof of principle level. And this is something that I personally learned a lot of things at the NKI on this particular matter. And there's also an issue of maintenance. How are you gonna, even if you develop a solution, how are you gonna hold this knowledge, since researchers are probably, maybe they're gonna leave at some point. So who's gonna carry the project? So at the NKI AVL, they have a lot of interest in implementing things, I would say. They have a lot of teams, first of all, to implement things. And I was especially intrigued by the team led by Dr. Thomas Jansen, who's a medical physicist, and he was a project leader. And the idea of this group was a data science was exactly that, to perform research on machine learning and analytics, but also implement the clinic. So we didn't focus so much about publishing. We did publish at the end, but the point was not to be the first primary goal. The other nice thing I found at the NKI was a diverse team of people. So I worked with, this was the core team of the people I worked with. So it was Thomas and Volker, who are medical physicists there. I worked very closely with Herbert Beamster, who is a software engineer, and he had dedicated time for this project, as well as with Patrick Gonzalez, who was a data scientist. And part of the team were clinicians as well. Kasper Karbat, he was our expert radiation dosimetrist, and Ola Hamming was our expert MD physician. And we also had Rita Simoes as our AI expert to work on the projects. So if we were to focus now on what we can do in radiotherapy, you definitely know these 4 major steps in radiotherapy: patient simulation, then followed by contouring, followed by planning, and followed by treatment. And these have been there for quite a long time, and I think they will still be there for many years. But we are under the transformation of this workflow a little bit. We already have several commercial softwares in auto-contouring, in auto-planning. And now I have also this other auto-adapt label there, trying to signify things that can happen also in adaptive radiotherapy. And all this automation, which is not necessarily machine learning, but machine learning can play a big part of it, of course, offers the possibility to speed up these steps. And it's not unreasonable to say that in a few years, these steps might merge into one step. It's not so difficult to think that we will have soon enough very good auto-contouring solutions and auto-planning solutions. And if we can speed this in the matter of minutes, then we can also adapt the treatment very fast by going back to the auto-contouring and auto-planning. So while this was happening, one of the first things we did with Thomas was to think and brainstorm about where exactly now a data science team that is in the clinic can help. And before I get into the details of what we actually did, it might be instructive to have a sneak peek on what is happening in other industries. So in the automobile industry, of course, it's not about auto-contouring, it's about autopilots, right? Self-driving cars, it's their goal, it's what they're doing. And this is an accident that happened some years ago. Apparently they're getting quite a few of those from a Tesla car that had an autopilot system. What happened in this case, I believe the autopilot system was on, the driver was not paying attention. He was playing a smartphone video game, and the car smashed on a barrier. It confused probably this highway lane, did the barrier triangle area with a highway lane and accelerated instead of putting down the brakes. And one of the things that the report mentioned as major cause was that Tesla didn't have at the time a collision avoidance system that was designed to detect such a crash, and also didn't provide an effective means for monitoring the driver's engagement. So this is useful for us because we are sort of in the same now game of trying to automate things, have like an automated driver for contouring and for planning. So one thought would be to build a parallel workflow of quality assurance procedures, basically. That's maybe what we need, intelligent QA systems. And we can have an auto-contouring QA, an auto-planning QA, an auto-adapt QA, which can be seen as programs, as a comprehensive QA program. And that's very good actually for the medical physicists because we know very well how to establish such a QA programs. It's just that we need to now focus the attention on software specifically around AI solutions. So in particular, we spent most of our times in contouring since we thought that this is a time-consuming part still, radiotherapy, and there's a lot of uncertainties. And I'm going to try to give an overview of 3 of the main modules that we designed and developed at the NKI: the anomaly detector, the symmetric impact predictor, and the uncertainty predictor. So I'll start with the anomaly detector. So what is the problem that we're trying to solve? Well, let's assume that we have a contour that is predicted by a software, an auto-contouring software, for example. In this case, you see a parotid gland for head and neck patients. And then right now, maybe a clinician will check this and correct the contour. And that's, of course, one QA process. We noticed that a second clinician may have actually a different opinion. And if he or she was to decide, maybe we'll make a different decision. And when we looked at the data, we saw that at least at the NKI, approximately 95% of our auto-contoured parotid glands were eventually corrected, which took time and raised the question, why were there so much corrections on this? Does the auto-contouring software produce anomalous structures, or are we overcorrecting? So the purpose of this was to develop an anomaly detection system that will notify the clinician if a contour needs corrections, so it can be considered anomaly, or not, so it can be considered normal. And the main algorithm that we used here was a tree-based method called isolation forest. And isolation forest basically is a special case of random forest as a machine learning algorithm, which is very popular machine learning algorithms used in many industries and many applications. But in particular, in this case, what you're trying to do is try to isolate a data sample by random splits in the feature space. So if you have like a 2-dimensional here feature space, you start doing these orthogonal slices, splits of your feature space. And if a data sample is somewhere here, for example, you will need a lot of splits in order to completely isolate it from the rest. While if it's somewhere here on the bottom right, like x sub 0, it's definitely easier to isolate with fewer splits. That's basically the idea here. And for features, we investigated a little bit of what exactly defines a contour, why something is a parotid. So first of all, there's a morphology to things that needs to be respected. So we extracted a lot of shape features that had to do with the volume, the length, the kurtosis, the skewness, and many other statistical metrics. But you also are interested in imaging features because imaging was used to delineate. And in particular, what we derived here was in the boundary. We looked at the contrast metrics that were sampled within a 3mm boundary ring. And there we sampled the mean intensity, energy, entropy, and other radiomics, as they call them, features. We did that on the original, the gradient image. And we also added distance features to the body contours, such as the minimum, centroid, and average distance. So in total, we had a 56 dimensional feature space. The other nice thing was NKI, we had a lot of data to work with. We had more of 1,000 head and neck patients that we can use. And here we followed a very general recipe. We kept 70% of the data for training and cross-validation. And then cross-validation starts already becoming a little bit difficult for an anomaly vector because you don't have labels. It's an unsupervised machine learning algorithm. So for cross-validation here, what we decided to do was to randomly contaminate some samples by doing a feature perturbation. So basically we tweak values of the features intentionally and throw them in our training data sets. And at the end, you get this type of histograms that they can identify anomalies by high negative values in this case, or you're more in the normal region if you're more in this right Gaussian shape part of the distribution. The difficulty is, where do you draw the line? Because I draw a line here, but where do you draw the line? What do you consider anomaly and what not? And then, of course, okay, let's say you do that. How do you validate that this actually works, not on perturbed features, but in realistic cases? You don't have realistic cases because nobody labeled something as anomaly in the clinic. So it's an ill-defined problem to begin with. But one solution you could do here is to develop your own synthetic anomalies. And this is one part of the project that I worked a lot with the clinician, and we sat together and we discussed about situations that happened in the past in the clinic. We found cases that were anomalous and the treatment continued, however. And we designed a spectrum of possibilities of what can happen. So this could be as simple as simple translations or rotations or expansions of the contour, or more tricky errors that could happen even more for the human intervention side, such as, for example, mixing up a label. The parotid gland right can be easily assigned to be a parotid gland left. And this will have an effect on the treatment. So we put that all together and we started calculating these ROC curves at the end. And in this case, we also investigated which features were actually differentiating better between anomalies and normal structures. And what we got as a final result were very good results if you used all the features or only image features. So morphological features had less of differentiation power, with an area under the curve here of 0.93 and 0.94. And this is specifically for the parotid gland that I'm showing. And then to decide that line, where do you draw the line? What is your decision threshold to say to the clinician? We thought, okay, the safest approach, since we want to implement this in the future, is to say, I'm going to put the line as low as possible to catch as much as possible anomalies. So prioritize more the true positive rate. As a trade-off, you're going to increase a lot the false positive rate, of course, when you do that. But that basically means that the system will flag more anomalies for normal structures. So it will be more time-consuming for the clinician, but you are on the safe side. And these are some examples of the depicted anomalies that we had, and I think it was quite interesting to see these examples while the algorithm was running. So here on the left, with the red contour, you see the auto-contour solution, right? If we had left it in an autopilot mode, this is what it would have treated there. And of course, it's completely different than reality. The reason for that is because patient positioning was different. So some patients, some head and neck patients in particular, they cannot lie flat on the table. They might need to have a different position. And something that is as simple as that, so clinicians know how to account for that, the autocontouring software did not, but it did still give an answer, which is where the danger, let's say, lies. Other cases will be crossing bone areas, even a little bit. You can catch them very easily with such a solution. And a third case I'm showing here on the right, this is the primary tumor. So this was a really big anomaly according to the system, but the gland was perfectly correct. The reasoning, of course, here is that we're very close to this tumor and especially the markers within the tumor. And this is seen as an anomaly. So this is quite interesting because indeed, this is an anomaly. This doesn't happen for every patient. Maybe it's rare, but it's not wrong. So this is to say that an anomaly is not always an error. So at the next step, what we tried to do was to introduce then a clinical pilot of the system. So we created a visualization app where we could investigate. We can use this in real time. The clinician could see in the dashboard. If you get a red bar, this means that it's anomalous. If you get a green bar, it's okay. You can look at historical data and histograms here to compare where your current situation is, and also a time series graph that can show you a trend, which is also quite important because maybe something changed in your clinical practice and now everything's becoming anomalous. So this identifies that something changed in your clinical practice. You have to investigate further. We run this pilot for about 6 months with the clinician giving us feedback. The clinicians were actually quite happy with the software. They liked this red and green flag system that worked in parallel to their own work. So it was not really implemented per se in the clinic, but it was implemented parallel to the clinic. And I'm going to come back to that later on. But following this project, then we thought, okay, what do we really care about? Do we care if a contour is exactly correct, or do we actually care more about what's happening in the symmetry? So, and this is a project that actually Rita Simoes and Patrick Gonzalez worked on. So what is a good contour? In radiotherapy, a contour would serve two purposes: to make a treatment plan and to evaluate the dose in the organ that it presents. And what we can do to evaluate what is the impact now of a potential erroneous contour is to either look at what is the symmetric differences between two plans, one plan that was using the clinically corrected contour and the other that used the auto-contour. But then you evaluate on the clinical contour, you evaluate on the ground truth, or you can have a dissymmetric impact on evaluation. So in this case, you keep the plan the same, and then you compare the dissymmetry between the two different contours, the auto contour and the clinical contour. So these were the deep and die metrics that were defined. And what is the dissymmetric impact on the true parotid, for example, when the auto parotid is used for planning? This is what we wanted to see more. And this is an ongoing project. It's not yet on the clinical pilot phase. But what Rita and Patrick are working is how can we explain the dye in the parotid? If we can hypothesize that there are some specific circumstances that are going to lead to a large dissymmetric impact on evaluation, then we can quantify that, and perhaps we can predict then the dye metric. For example, the large geometrical differences in the direction of the dose gradient are expected to give a high value of dye, and a large volumetric changes in high dose regions as well. So if you have this ground truth and you have the auto contour as well, you can have all these editing vectors that you see here. And of course, if you know all these editing vectors, then actually your problem becomes trivial because you can just correct the contour and then just plan on the correct contour. But the question we sought here to answer was, what is the minimal description of the local contouring error that will be necessary for an accurate prediction of the dye? And at this phase, so this is still in the early phase, but Rita and Patrick, they had worked on 94 head and neck patients, and what they did is they used a portion of the editing vectors, starting from 0.5% up to 100%, and they try to quantify now as a performance metric the mean square error of the dye on the parotids and on the brainstem. So they looked at two different structures, one with a mean dose criterion and the other with a max dose. And these are some of the first results, but in general, we're seeing that we don't need all the editing vectors in order to make these predictions quite accurately. So you need a portion of those only, and you can get similar mean square errors. And then I wanted to continue more in the uncertainty prediction. So before I do so, a few thoughts about decision making, because it's all about decision making, I think, in this context. And what we presented with an anomaly detector, for example, is a pass-fail system, which utilizes hard evidence. So it's really a data-driven approach, as we say. And it is an algorithm that is trying to give you a binary outcome for your decision. It's either a red flag or a green flag. It's very technical, and it's very simplistic in a way. So it's really a matter of, if the score is larger than the threshold, then you pass, otherwise you fail. However, if we think of what a clinician would do, they do much more things than that. They utilize visual information, they reflect on past experiences, they have a personal knowledge of the subject, they have group opinions that perhaps sometimes they bias their views of things. So it's a much more cognitive process. Clinicians think with scenarios, they don't think with just a score based on an image. And again, if I was to look a little bit what other industries are doing, they have sort of recognized this problem of binary outcome models. So instead of suggesting to have an autopilot and you play with your smartphone or you read a magazine, instead you can have the driver and the AI engaged all the time, and the AI system can support the driver using some uncertainties and probabilities. So it can suggest things based on probabilities, but then the driver has the liability of the final decision. And it's a much more cognitive also process, because you can think of very nice visualizations to do so. So probabilities and uncertainties in neural networks in particular is a very hot topic in AI right now. If you go to a conference that is a focus on AI, I'm sure half of the talks are going to be about that. And adding probabilities and uncertainties adds a new dimension on these treatment decisions. It enhances critical thinking, and it allows not to make any automated decisions. So I would even say that it might be easier to lead to clinical implementation because of that exact reason. Now, this is not a new topic. This has been studied for many years in the past, and I'm not going to go into the details for neural networks. I'm sure you've seen many talks explaining neural networks, but the basic idea of how to introduce uncertainties in neural network is when you're optimizing such systems and you're trying to find the best values for your weight matrix, you don't go for just one fixed value, but you prefer to have a distribution. So if in every of these weights you had actual distribution, then you can propagate this to your prediction label, and then you can calculate a standard deviation, for example. However, in practice, there are ways that you can do that, but it has been shown that it's difficult to do this inference in practice. At least that was it until recently, where somebody thought of using the dropout technique. And the dropout technique actually was suggested by Hinton et al. 2012 as a way of reducing overfitting in neural networks. What basically you're doing with dropout is you have this network, and then during training here, you decide to randomly switch off some of the nodes per epoch, and then on the next epoch, you switch off some other nodes. So every time you're training on a sub-network, let's say, and this gives the possibility of having a network at the end that has not been overfitted. But then Kendall and Gall suggested in 2018 that what if we use that at inference phase, or when you're trying to make a new prediction, at test time also, as it's said, and you do this switch on and off every time, and every time you get a new prediction based on a subnetwork of your network. In another way of seeing that is that every node here, it becomes Bernoulli experiment that you turn it, it's either going to be 1 or 0, and you do multiple of those experiments. So, and every time you have a new sample. And for those that have already figured out, this is basically Monte Carlo sampling. So this is what it's called. It's called the Monte Carlo sampling approach. So so this would be a basic unit architecture that I'm sure also you have seen many times, and I'm not going to explain again here, but this is the state of the art, as they say now in neural networks, for image segmentation. So if you were to start with that, and there's many libraries that they offer that right now, and it's quite easy to implement that one in the clinic, then you can apply this Monte Carlo dropout technique. So during test time, you randomly switch on and off some of these nodes, and each time you're getting a new prediction, which is going to be a little bit different than your previous one. And then if you have multiple predictions, then you can go by a voxel and sum the output of the voxel, and then you divide by the number of Monte Carlo samples you had, and now you have a probability map. So you don't have just a binary decision, you're actually getting these probabilities. And it's easy to go a step further. Since you have probability per voxel, then you can calculate the entropy as well, which is a measure of uncertainty. So this is an example of another app that we made, which was, again, here I'm showing the parotid glands. And here I'm showing on the top left, the clinical target. So this would be the ground truth, what the clinician contoured. Let me stop it so I can explain it a little bit better. On the right is the error map. So this would be the error that the autocontour system made compared to the clinical contour on the left. And on the bottom, you see the probability map. Highest value means that it's much more probable that this is a parotid, and lower values, it's much less probable. And then on the bottom right, it's an entropy map, calculated as I described before. And you can already appreciate perhaps that most of the entropies values, the highest entropy values, are actually in the boundary of the structure. And if we move a little bit forward here, we start getting some interesting insights of what exactly is happening when you are contouring a parotid gland. Here, for example, we're getting some error on this tail. Something has been contoured here that the autocontour system didn't contour that exact thing. And indeed, though, in the entropy map, it recognizes that something is happening in that corner. They are high uncertainties. It's just that it was a lower probability, so maybe that's why it was not segmented. And this, again, if you talk with a clinician, perhaps here was even more visible. If you talk with a clinician, they will tell you immediately what's happening here. Some of the symmetries would decide to contour a duct here as part of the parotid gland, while others, they would consider that this is not part of the parotid gland. So immediately we're getting insights of what is our clinical practice and what is our consensus. I have another example to show you in this that I found interesting. This was in the case of CTV lymph nodes, and this was a work that we looked a little bit with Olga Hamming, our physician. And again, here you see, of course, the entropy maps are much higher. It's a more difficult structure to contour. And you're going to start seeing here that we're getting a lot of uncertainties on the anterior sides that correlates very nicely with the error maps as well. And this is really wonderful because the error maps, you don't have that in real time. You don't know what is the error of your system, unless if you manually go and correct all your contours. But here you have an entropy map that the same system can tell you that, yes, I didn't contour this area, but I know that some people contour it, or that there are uncertainties in the model, so you could potentially contour it. And the same thing happens then later on when we are moving downwards, more closer to the posterior side. You're going to start seeing more uncertainties and a longer tail on the entropy map here. And again, here the probabilities are low, so the autocontour system probably not contoured that, but it does recognize that I'm having a lot of uncertainties here. That's what it tells us. And this, I think it's fascinating. Another thing I found fascinating was that when I talked with the physician and asked her, she immediately picked up what was happening. So basically, there were three different categories of how you contour CTV lymph nodes, depending on where the tumor is. So she immediately said that this is happening because these categories are mixed in this training set. So this, in my mind, proves the point of how important it is to work with a clinician side by side on this project. So this was my talk, and this was an overview of the projects. I tried to be not too technical and give you a glance of what I did. Some lessons learned as a final slide from my side, trying to bridge this gap between research and clinic. First, maybe is identify the minimum viable product. So this is very important. There's a lot of things we can work on, but if you do work on something that doesn't exist in the clinic and you have the data for it, then go for it. Another thing is think ideas that minimize workflow disruption. So, for example, an autocontouring system is a very disruptive technology, right? It literally suggests that you can replace someone in the clinic with this software, if this software is perfect. But, and this, of course, might be true eventually, but in the meantime, if you want to implement things, it might be easier to think of parallel workflows. So the anomaly detector, the uncertainty predictor, as QA systems, I think they maximize the possibility of implementation because they work in parallel to the clinical workflow. They don't stop the physician or the dosimetrist to continue doing what they were doing before. A third, maybe a suggestion, forget about publishing. No, okay, I don't mean it completely, at least at the beginning. So this is a mindset, perhaps advice that it's good to think about implementing, and it's very likely you're going to publish at the end, so you can have both worlds. Solve the problem of deployment service and connect the data. This is a humongous problem in hospitals. Everywhere. At the NKI, we had teams to help us with this, but still it was difficult. And following that, hire software engineers. I was very lucky to work with a very talented software engineer and helped me to be a much better programmer myself, but also help to really build all these pipelines and these engineering steps that are required. As I said before, make the clinician part of the development team. This I think is part of the success of a success story, because a clinician that is part of the development team not only improves your product, but also is the end user. So it's much more likely he or she will use your app if they co-developed it. Invest time in visualization apps. This is something that I maybe in retrospect should have done earlier. Start with a visualization app, even of simple statistics. The moment people have visualization apps, they immediately connect with the product. They like it much better. Nobody's going to go on terminal and run your Python script. So make things look nice. And then finally, don't seek perfection. Implement something fast and iterate, as they say now in Agile, using another of the buzzwords of these days. So thank you again for inviting me for this talk. And I would like to thank all these people I had the pleasure to work with at the NKI, especially Thomas, that we had very similar thinking, I think, in radiotherapy, but also Volker, Patrick, Herbert, Rita, Casper, that were really the core team of people that I would work every day.